Pluto, a distant and confusing, more modest planet, was once a singular member of our solar system's planetary family. However, later disturbing announcements by leading astrophysicists Neil deGrasse Tyson and Michio Kaku brought Pluto back into the spotlight with a shocking revelation. They propose that this icy world is on a potential collision course with Neptune. But how could this happen, and what might be the consequences of such a massive event? Are we witnessing a fascinating cosmic phenomenon, or is there more to this impending celestial collision? Join us as we explore the potential outcomes of a Pluto-Neptune crash. Pluto, a former planet that was downgraded to a dwarf planet partly due to its peculiar orbit, remains a subject of interest and study in the cosmic community. According to recent predictions by leading researchers, Pluto's trajectory is dangerously close to Neptune's. Astrophysicists Neil deGrasse Tyson and Michio Kaku are both raising the alarm about a potentially hazardous collision between these two planets, which could pose a massive threat to Earth. But how is such an event even possible? Pluto's journey around the Sun is unlike any other planet in our solar system. It takes a staggering 248 years to complete a single orbit. This means that since its discovery in 1930, it hasn't even completed one full revolution. However, the intrigue doesn't stop there. Pluto's path is marked by its highly elliptical shape, veering entirely from the nearly circular orbits of the major planets. What makes Pluto's orbit even more surprising is its inclination, measured at 17 degrees to the ecliptic plane. The path Pluto follows is much steeper compared to other planets. This inclination and eccentricity add layers of complexity to its orbital pattern. One of the most fascinating aspects of Pluto's orbit is its interaction with Neptune's. For about 20 years in each orbit, Pluto actually moves closer to the Sun than Neptune, defying what we might expect from their positions in the solar system. This leads to the natural question: why hasn't Pluto crashed into Neptune? The answer lies in the gravitational effects of other planets. The study of Pluto's orbit began soon after its discovery. Initially, astronomers struggled to grasp its unique path. Unlike other planets whose orbits lie fairly close to the ecliptic plane, Pluto's orbit stood out with its steep inclination and unpredictable shape. The mystery deepened with the realization that Pluto's orbit does, in fact, cross Neptune's. The stability of Pluto's orbit amidst these complexities is evidence of the intricacies of celestial mechanics. The three-body problem in space involves figuring out how three objects, like Pluto, Neptune, and the Sun, move and influence each other with their gravity. It's like trying to predict where they will go based on where they start and how they pull on each other. In Pluto's case, this problem shows how its path, Neptune's path, and the Sun's gravity all coordinate in a complicated manner. Terms like asymptotic libration and degree libration, along with the VSK oscillation, are part of this puzzle. According to astrophysicists, what's keeping all planets in their orbits is a sort of libration. Regarding Pluto and Neptune, this term means that whenever Pluto crosses Neptune's orbit, its position is always at least 90 degrees away from Neptune. This spatial separation is crucial in keeping their orbits from colliding. Extension libration, on the other hand, refers to the vertical movement of a celestial body in its orbit. For Pluto, this means that when it comes closest to Neptune or any other giant planet, it is positioned far above their orbital plane, offering an additional layer of protection from potential impacts. Another critical factor in this situation is the VSK oscillation, named after three researchers, Vav, Mac, LV, and Kai, who studied how objects move in space. This oscillation helps explain why Pluto's path around the Sun is so odd. Despite seeming chaotic, this oscillation helps keep Pluto's orbit stable over an extraordinarily long period. The VSK oscillation shows that although things in space may seem wild and random, certain patterns and rules keep everything in place. These factors help maintain Pluto's orbital stability, ensuring it doesn't crash into Neptune or veer off course. This three-body problem aids in understanding how orbits change due to how space objects pull on each other. Studying this helps us learn more about Pluto, our solar system, and distant stars and planets. Numerical simulations in the late 1980s revealed that despite these stable properties, Pluto's orbit is inherently chaotic, with minor deviations in initial conditions leading to significant differences over millions of years. However, these strange properties of Pluto's orbit have been found to maintain stability over extraordinarily long time scales, effectively managing the chaos. Recent computer simulations have helped us understand how giant planets like Neptune, Jupiter, and Saturn influence Pluto's orbit around the Sun. Neptune has a special relationship with Pluto. For every 2 orbits Pluto makes around the Sun, Neptune makes 3. This resonance helps keep Pluto's orbit stable. However, Neptune isn't the only one helping. Jupiter's gravity also plays a significant role in stabilizing Pluto's orbit, and Saturn contributes overall as well. These simulations show that Jupiter's gravity alone is strong enough to ensure Pluto stays on a steady path for an incredibly long period, possibly even billions of years. Perhaps Neptune, Jupiter, and Saturn are working together to ensure Pluto can continue moving safely in space without running into trouble. These peculiarities are vital in the broader context of the universe for maintaining the order and stability of celestial bodies' movements. Without these factors, the solar system as we know it would be a place of far greater chaos and unpredictability. Bodies like Pluto could potentially collide with others or be ejected from their stable orbits, causing a chain reaction affecting other celestial bodies. For Pluto, especially with discussions about it potentially crashing into Neptune in the future, understanding its orbit is essential. This provides a clearer picture of the solar system's dynamic nature. The case of Pluto demonstrates how even the most seemingly unstable orbits can achieve a state of balance through the complex interplay of gravitational forces and orbital mechanics. It also highlights the importance of continuous observation and investigation of these phenomena to better understand our place in the universe. Exploring the depths of space often leads us to confront the unpredictable nature of celestial bodies, and Pluto's orbit is a perfect example of this unpredictability. The concept of orbital chaos, which refers to the sensitive dependence of a celestial body's orbit on its initial conditions, is clearly illustrated in Pluto's case. This means that even slight variations in the dwarf planet's position or speed can significantly alter its long-term orbit. Using computational simulations has been incredibly helpful for researchers trying to figure out how Pluto moves through space. These simulations use complex mathematics to model how Pluto, along with other space objects like Neptune, interacts gravitationally. By adjusting small details in the simulations, astronomers can see how even tiny changes can have a major impact on where Pluto ends up. In the late 1980s, these simulations revealed something fascinating about Pluto's orbit. Despite having mechanisms like asymptotic and latitude libration to keep it stable, its orbit can still be wild and unpredictable. Even a minuscule difference in where Pluto starts or how fast it's moving can lead to a completely different trajectory over many years. However, despite this chaos, Pluto's orbit remains stable for a very long time, billions of years. This means Pluto's journey around the Sun has a kind of order, even though it seems chaotic at first. Predicting cosmic events, especially when they involve chaotic orbits like Pluto's, presents immense challenges. The inherent unpredictability of these systems means that long-term predictions are often filled with uncertainties. While mathematical simulations provide a strong basis for understanding and predicting the future behavior of celestial bodies, they also highlight the limitations of our predictive capabilities. These models rely heavily on the accuracy of initial conditions and the complexity of the interactions they simulate. Any slight inaccuracy or distortion can lead to vastly different outcomes, making precise predictions a daunting task. Moreover, the chaotic nature of celestial orbits like Pluto's reminds us of the ever-evolving and dynamic nature of the universe. While we have made tremendous strides in understanding space, the case of Pluto reminds us that our knowledge of the universe still remains limited. Understanding the gravitational effects of the giant planets on Pluto's orbit provides valuable insights into the broader dynamics of the solar system. It shows how the presence and position of each planet can have far-reaching effects, influencing the stability and trajectory of other bodies within the system. So, why are prominent astrophysicists only now raising concerns about a potential collision between Pluto and Neptune despite all these complex forces working to prevent such an event? Neil deGrasse Tyson, a renowned astrophysicist, offers a unique perspective on the mysteries of our solar system, particularly the intriguing case of Pluto. Tyson, known for his role in the reclassification of Pluto from a planet to a dwarf planet, provides insightful commentary on the evolving nature of celestial mechanics and the public's fascination with the unexplored reaches of space. Tyson's stance on Pluto's reclassification is rooted in the ever-expanding understanding of the universe. He emphasizes that as scientific knowledge grows, so too must our classifications and interpretations of celestial bodies. The story of Pluto serves as a testament to the dynamic and ever-changing nature of space exploration. Tyson's perspective highlights how scientific advancements reshape our understanding of the universe. Pluto's reclassification from a planet to a dwarf planet was not an attempt to diminish its importance, but rather a reflection of the evolving criteria used by astronomers. As new discoveries are made, our understanding of the solar system becomes more precise, prompting necessary adjustments in classifications. Similarly, physicist Michio Kaku has shared his thoughts on the complexities of planetary orbits and gravitational interactions. He emphasizes that while Pluto and Neptune seem destined for a collision when viewed superficially, the intricate dance of celestial mechanics prevents such a catastrophe. Kaku often explains how gravitational resonances, orbital inclinations, and the three-body problem work together to maintain stability in the solar system. Despite these assurances, the possibility of orbital shifts caused by external cosmic events, such as passing stars or rogue planets, remains a theoretical concern. Even a slight gravitational disturbance from a nearby star could disrupt the delicate balance of the solar system, potentially altering Pluto's orbit or even affecting Neptune and the other outer planets. The discussion of a potential Pluto-Neptune collision underscores the complexities of celestial mechanics and the limits of human understanding. While current simulations show stability, the chaotic nature of Pluto's orbit means that future predictions come with inherent uncertainty. Astrophysicists continue to use advanced computer models to simulate potential scenarios involving Pluto and Neptune. These models consider countless variables, including gravitational influences from the Sun, Jupiter, and Saturn, as well as the possibility of unknown forces from the distant reaches of the Kuiper Belt. The Kuiper Belt, a vast region of icy bodies beyond Neptune, is where Pluto resides. Its gravitational interactions with other Kuiper Belt objects add another layer of complexity to understanding its orbital behavior. Collisions or gravitational tugs from these distant objects could, in theory, alter Pluto's trajectory. Despite these potential hazards, current research indicates that the likelihood of a collision between Pluto and Neptune is exceedingly low. Their orbital resonance ensures that they remain in a stable, synchronized relationship, passing each other harmlessly despite their intersecting paths. The case of Pluto and Neptune serves as a profound example of how the universe balances chaos with order. While their orbits appear chaotic and unpredictable when viewed in isolation, a deeper analysis reveals a finely tuned gravitational system that has persisted for billions of years. This intricate cosmic choreography reminds us of the immense complexity underlying the universe's seemingly random behavior. It also highlights humanity's ongoing quest to understand the forces that govern the motions of planets, stars, and galaxies. Looking ahead, astronomers will continue observing and simulating Pluto's orbit, using ever-improving technology and data from space missions, such as NASA's New Horizons, which provided an unprecedented close-up view of Pluto in 2015. These observations will enhance our understanding of how Pluto interacts with Neptune and other celestial bodies in the outer solar system. In conclusion, while the prospect of a Pluto-Neptune collision may capture the imagination, Current scientific understanding assures us that such a scenario is highly unlikely. The gravitational interplay between the planets, guided by the principles of orbital mechanics, keeps the solar system in a delicate but enduring state of equilibrium.